There are a few important topics in Chapter 10, but I think that Chapter 11 is a bit more involved, and I wanted to get to that sooner. So I'm going to try going over Chapter 10 as a video here. The first section goes over naming, and we've been using halogens as substituents in all of our naming sections, from alkanes to alkenes to alkynes. So maybe review some of your other chapters from last semester on how to name alkanes, and then you'll know how to put the halide on as a substituent, a chloro or a bromo or a iodo or fluoro group, wherever the substituent is. So the use of the letter X is something new. If we just want to say there's a halogen here and we don't want to say that it has to be bromine or has to be iodine, then we might just put the letter X. So you might see that a little bit as well. The halogen bond to carbon behaves as a polar bond, even if the electronegativity value itself does not seem to be high enough to be pulling electrons away from carbon. The larger halogens have lower electronegativity scores, but are polarizable, and so the bonds do behave as polar bonds with the negative charge on the halogen, partial negative charge on the halogen, and the partial positive on the carbon. One of the ways that you can make an alkyl halide is from an alkane. It's not the best way to make an alkyl halide, but it is one of the few things that you can do with alkanes. Alkanes can be burned. You can use them for combustion. That's very economically important. And they can also be halogenated with a halogen and some sort of radical initiator, like light. That's a very good radical initiator. The only thing is that you tend to get a mixture of products. So if you're doing this on a huge scale, just to try to make some alkanes more synthetically useful, and then you can separate out all the products and sell bottles of them, that's where this is used more. Actually, in the lab, when we're only doing a little bit of reaction, we don't use this reaction as much, but it is good to know about it. It's a good review of radical reactions. So a lot of times we've been doing these polar reactions where the bond cleaves heterolytically. The one atom will get both of the electrons that was in a bond. The radical reactions, you have what's called a homolytic bond cleavage, and so the bond, which is two shared electrons, splits equally, and each atom that's participating in the bond gets one of those electrons. And so we're using those single barbed arrows. So your mechanism arrow will look like this with one barb, rather than like this with two barbs. This is two electrons moving. This is just one electron moving. So these radical reactions have a cycle. You need something to start the radical chain reaction. That's an initiation where you have a regular bond splitting homolytically, so that two atoms have these radicals, unpaired electrons. This unpaired electron is very reactive. These radicals go around and react with other sigma bonds, and they produce another radical and another new bond that forms as a product. So there is a radical as a product, which is also very reactive. So the propagation step just keeps things going. You still have a radical, it's just a different one. And then if you have two radicals that meet up and join, that would form a sigma bond, and that would stop the cycle, because once you have a sigma bond, that is not nearly as reactive as a radical, and so the sigma bond is not going to go attacking anything else. So that sort of stops the process. Visually, here's some examples of what these look like. The initiation step with the two single barbed arrows showing that the two electrons are breaking apart. You have two atoms with radicals on them, unpaired electrons. Either one of these could attack a sigma bond. So here we have this bromine radical attacking a carbon-hydrogen bond. The bromine radical and one of the electrons from the sigma bond are used to form this new bond. Here's the new bond being formed from those two electrons. The other electron that was in this carbon-hydrogen bond just lands on the carbon. So now we have a carbon radical, so a carbon that it's not charged but does not have the full octet of electrons, so it is very reactive. I've drawn a little review of what carbon looks like in these various reactive configurations. So a carbocation down here, carbon would have 3 bonds and no lone pairs. Each of these bonds, the carbon is sharing those bonds, so the carbon has 1 electron from each of those bonds. That gives it 3 electrons, giving it a formal charge of +1. That's why this is what carbon looks like when it is positively charged. It is a cation. The shape of that is planar. We've looked at these before last semester. We've also looked at carbanions. Carbon with a negative charge would be carbon with 3 bonds and a lone pair. That gives it 5 electrons when you count up that formal charge. 1, 2, 3, 4, 5. 1 from each shared pair, and then 1 or 2 from the lone pair that's just on carbon itself. So that is 5. Carbon has 4 valence electrons usually, so this is 1 extra electron. It is a negative charge. The shape of that, to make room for those 2 electrons, that lone pair, is usually tetrahedral. We did learn about an exception last semester. If that carbanion is part of an aromatic ring, then those lone pair and the lone pair is needed for the pi system, it could be planar in that case, but usually it's tetrahedral. The carbon radical is not charged because if you count 1 electron from each of these bonds plus the 1 unpaired electron, you end up with 4. That is what carbon should have, so it is not missing an electron. It is not does not have an extra electron. It just is reactive because it does not have an octet. If you count the shared electrons 2, 4, 6, and then this one, it makes 7. So it does not have the 8 electron octet. So that makes it very reactive, but it is not charged. It is also planar. It tends to have that 1 electron occupying a p orbital, and the other bonds, the sigma bonds, are being formed by sp2 hybridized orbitals. So one significance of that is that if you do form a radical, if this carbon did have a stereocenter, if it was a tetrahedron with a stereocenter, when you form the radical, that stereocenter is lost because this is now a flat carbon. It can be attacked from either side, or it can attack from either side. Okay, so back to our propagation steps. We have this reactive carbon radical that can attack another sigma bond. So this can attack another bromine molecule that might be in the mixture. We have bromine and light being added to an alkane. So we have some bromine around. This 1 electron plus 1 of the electrons from the bromine-bromine bond will be used to form a carbon-bromine bond. That will leave the other bromine atom as a reactive radical to go back and start the cycle. So we have an alternating, the bromine radical comes in, carbon radical comes out, then the carbon radical comes in, bromine radical comes out. And then step A can be repeated, or I guess these are A and B. So if we call this steps 1 and step 2, we can just keep going back and forth. Step 1 happens, then step 2, then step 1, then step 2. So this keeps going and going in a cycle so that many alkyl halide molecules can be formed. Then there are lots of ways to break this chain, break the cycle. If 2 bromine radicals find each other, they will just make a bromine molecule, and that puts an end to the radical reactions until if this bromine bond breaks with light again and forms 2 bromine radicals again in like an initiation step, then that could start some more. But this particular step stops the cycle. Another way to stop the cycle is if the carbon radical finds a bromine radical rather than finding a bromine molecule, those 2 will just form the bond, and there is not a bromine radical created as a second product in that particular example. Another thing that could happen is that 2 carbon radicals can find each other and just form a regular sigma bond there. The halogens that are usually used for this type of cycle are chlorine and bromine. Fluorine ends up being too reactive to be useful, and iodine tends to be not reactive enough. So it is more economically useful to create alkyl halides from chlorine and bromine, and then there are other ways to make fluorides and iodides. So if you tried to do this on 1 mole of alkane and 1 mole of bromine, you would get a mixture of some of the alkane having many halogens on them and some of the alkanes having no halogens on them. So you would not be able to control that each alkane is getting 1 halogen. And so usually you use an excess of the alkane. So you would use, 3 or 4 moles of the alkane and only 1 mole of bromine, and then some of the alkane would remain unreacted, but the alkane that did react would, for the most part, only get 1 halogen. So that helps control how many halogens get onto the alkane. And then we did already mention that the radical is planar, so any stereochemistry you have would be lost. Here we have some practice to try drawing all of the possible propagation steps for chlorination of propane. So let's see, chlorination of propane, what does that mean? So we have chlorine and we have propane. So if we wanted to add a chlorine to the propane, we could add it on the end, making 1 chloropropane, or we could add it in the middle, making 2 chloropropane. If we add it at the other end, then we have the same 1 chloropropane, it's just flipped around. So these are the 2 possible products, and we want to draw some propagation steps that lead to these products. The initiation step, the first step would be to make 2 chlorine radicals. So the initiation step has made some chlorine radicals, and we are doing the next steps, which are the propagation steps. So you can pause the video and try to come up with different propagation steps. Remember, that means that a radical goes in, breaks a sigma bond, creating a different radical. So I'll let you pause that. Okay, so let me go ahead and draw some of these propagation steps. What would happen is that this chlorine would come in. Let's do for the first regioisomer that I drew to make 1 chloropropane. Then that would mean that this chlorine radical comes in and interferes with this carbon-hydrogen sigma bond on the end of the molecule. So one way to draw this is this electron and this electron coming together in the middle of space. Another way to draw this, if you want, is to have the electron from the bond just go and land on the chlorine. And so there's already an unpaired electron there, so obviously this new electron is going to form a bond. Really, this top way is one that I've seen a lot more often. So, but either way, the other electron in the bond would land on the carbon. This is what you would end up with, a carbon radical and a molecule of HCl, hydrogen chloride. I'll put this guy in parentheses. That's the same thing, just a different way to draw the arrows. The other propagation step that would have to happen is for this reactive carbon radical to approach a new molecule of chlorine and to break that sigma bond by taking one of those electrons. So this radical would pair with one of the electrons that is in the chlorine-chlorine bond. The other electron that's in the chlorine-chlorine bond would go onto the second atom of chlorine here. So this plus is not a positive charge, this just means that you get both of these products. So you get both of these products from that step as well. So here we now have the product, 1 chloropropane, and then we have another atom of chlorine radical that can attack an unreacted molecule of propane and do this same step again. So we have like steps 1 and 2 that would alternate, making a cycle to make a whole bunch of 1 chloropropane. We would have a similar cycle to make 2-chloropropane. It's just that the chlorine radical attacks a different hydrogen on the molecule, one that's in the middle rather than on the end. So now this is the sigma bond that is being attacked. One of the electrons in the bond is going to go and make a hydrogen-chlorine bond. The other is going to go onto the carbon. Here is your result, a new hydrogen-chlorine bond, and then a reactive carbon radical in the middle of the chain here. The second step in the cycle here would be for this reactive carbon radical to disrupt a chlorine-chlorine bond, taking one of those electrons out of the bond. The other electron would go back onto, or would go onto the other chlorine atom. The result of this would be a molecule of 2-chloropropane and a chlorine radical that could be used to repeat step 1, making a cycle again. So altogether we have 4 propagation step possibilities. I've just numbered them 1 and 2 because it just kind of shows how it's a cycle here. I mean, of course, this chlorine radical could go and attack an end hydrogen and then make this, and then go up here and then make this. So you could have like a little figure 8 going, or you could have just some circles going here. It's just a cycle of different propagation steps here. Okay, so this first step in both of these creates a carbon radical. And the more stable the carbon radical, the easier it's going to be to create. And so the more likely that step will happen because it's easier to do. It takes less energy. And so here is a little diagram that shows the stability of these radicals. It is extremely hard to make a methyl radical or a vinyl radical, so that is not going to happen very much. If you had an alkene in the molecule, it would be much more likely that you would make the radical on the carbon next to the pi bond, giving an allylic radical. If you don't have any double bonds or benzene rings, then most likely you would make a tertiary or a secondary radical as a first choice before you would resort to having to make a primary radical. And so we don't get equal amounts of product formed. It's not like all of these sigma bonds between carbon and hydrogen are equally likely to get attacked. And so the probability of attack is not just based on the number of different hydrogens that are in that position, but also the relative rates of reactivity. How reactive is that hydrogen? What do we mean by that? Let's see if all of these hydrogens reacted equally, if they were equally probable to react, what would be the mixture of these two types of product here? How many of the bromine would be on the one in from the end versus the ones that are going to be on the end? So in order to get this product, you would have to react. In order to get this first product, you would have to react with one of these hydrogens that's on a secondary carbon. I'll draw them in blue. So if the bromine radical attacked one of these hydrogens, you would get this first product here. In order to get the second product, you would have to attack a hydrogen on the end. So to form the second product, you would have to attack one of the hydrogens that I drew in green. And I have drawn 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The formula for butane is C4H10, so I have drawn out all the hydrogens. So there are 4 different hydrogens that lead to the first product, 6 hydrogens that lead to the second product. So out of the 10 hydrogens that there are, 4 of them will lead to the first product. So you have a 0.4 relative chance of getting that first product, which is 40%. For the second product, that's 6 hydrogens out of the 10 that are in the molecule. So that is a 0.6 chance, a 60% chance of getting the second product. And so if all of these hydrogens reacted equally, you would expect to get these two products in a 40-60 mix. However, the hydrogens do not react equally because, as we said before, the radicals formed are not the same stability. So pulling off a blue hydrogen would lead to a secondary carbon having the radical. Pulling off a green hydrogen would lead to a primary carbon having the radical. And so we know that it is better to pull off the secondary hydrogen, leading to a secondary radical that is more stable. So how much more stable? So it depends on the temperature and the conditions of the reaction, but let's do an example where the reaction conditions made a secondary 82 times more likely to react than a primary. It would be fantastic if we had a tertiary carbon, but we don't, so none of that is going to form because that's not even a possibility. We have 0 times 1600, we're going to get 0 of that product. But we're going to have the number of hydrogens times the relative reactivity. So the relative reactivity for tertiary is 1600, but the number of hydrogens making that possible is 0, so we are not going to have any of that. Let's do the math for the other types of products, however. So primary was in green, so this is the primary. We have 6 hydrogens times 1 being the relative reactivity, so I'm doing this right here. I should have paused this. Let's have you, you can pause this if you want, see if you can figure out the number of the relative reactivity and the amounts of products that you can form from this reaction. Okay, in case you pause that, hopefully you got this, the primary hydrogens here. So we have 6 being the amount of this product. For the secondary, the number of hydrogens we decided was 4. However, the relative reactivity, it's 82 times as likely to react, 82 times more reactive. That makes 328. So for every 6 molecules of primary, I should put this over here. So there are going to be 328 of this 2-bromopropane formed for every 6 molecules of So there are going to be 328 molecules of 2-bromobutane formed for every 6 molecules of 1-bromobutane that form. So it's a 6 to 328 ratio. You could divide both of those by 6 and get a ratio. Let's go ahead and get percents. So the total amount of molecules that are forming is 334. 6 plus 328 makes a group of 334 molecules. Let's say we're talking about 6 of them are the primary halide, 328 are the secondary halide. So if we figure out the percents over here, out of that 334 molecules, only 6 are going to be the 1-bromobutane. 6 out of 334 represents about a 2% of the product being the primary halide, and then 328 out of 334 makes about 98% of the product being the secondary halide. Let's have you try another example of this with chlorine. The chlorine does not have as great a selectivity. It's more reactive than the bromine, and so we don't have as much selectivity in the reaction, so we only have 3.8 times as many secondary radicals formed as primary, not 82 times as many. So if you want to pause and figure out the percentages of product formed for this reaction, go ahead and do that. So here I've done a similar type of calculations to the example above. The primary, there are 6 hydrogens. The relative reactivity is 1, giving 6 molecules of this. 4 hydrogen possibilities times 3.8 amount of reactivity gives 15.2. There's not enough significant digits in the relative rates to go past the decimal, really. I just kept the 2 for the calculations and underlined the 5 and the 15. So these added together gives, out of every 21.2 molecules that react, about 21 molecules that react, 6 of them will be the primary, 15 of them will be the secondary. That represents a 72% formation of the secondary product, 28% formation of the primary product. So a lot closer than the previous example. It did occur to me that the previous example, I probably should have switched where I was writing the blue and the green. The secondary product is the one that is 98%, and the primary product is the one that is 2%. So hopefully no one was confused about that. The secondary is much more reactive here. So depending on the conditions, you can get different amounts, but generally you're going to get more of the secondary, or if there were tertiary possibilities, you would get more of that. I just had some energy diagrams that are interesting to take a look at. I was mentioning that something that is more reactive is generally less selective. If you think of someone as doing a task, with a lot of energy and rushing through and trying to do it really fast, then they're probably not going to be as careful. So that's what happens in chemistry as well. If you have something that's really reactive, you have conditions that the reaction is taking place too quickly, it might, there's a lot of energy there, and so the differences between these different possible activation energies is not that much compared to the amount of energy that the reaction has to take place. So if you have someone that's, chopping a vegetable really quickly, maybe the pieces aren't going to be all as even. So you're not getting very careful, very selective work over there. Whereas someone who's taking their time might be going slower, but creating more uniform pieces. So being more selective, being more careful about what they're doing. That isn't always the case, but it is a trend that we do see in chemistry, that if something is more reactive, it tends to have a lot of energy to be able to do all these things, whereas if something's less reactive, then it might only have enough energy to do one. And so you get a lot of selectivity for just that most favorable pathway. Another thing that you can notice in this energy diagram is that this is a exothermic reaction, and for exothermic reactions, the transition state tends to be more similar to the starting material. There's only one starting material, so the transition states are more similar to each other, whereas in the formation of the radical with bromination, it's an endothermic process, and for endothermic processes, the transition state tends to be more similar to the product. This is the formation of the radical, not the formation of the actual haloalkane, but so the radicals are different in energy, and so the transition states are more different in energy because they resemble the product rather than the reactant. And we did mention that this is more of an industrial scale reaction. Halogenation in a laboratory setting, because of this lack of selectivity and the difficulty in controlling the reaction, it's not something that you want to do if you only have a small amount of material to work with. A more selective, more useful way to make halogens or to make halogenated alkanes, haloalkanes, in the laboratory is to react a halogen with an alkene. We've already seen this last semester. I believe it was chapter 6. And we were looking at electrophilic addition of alkenes to something like HBr to get the bromine onto the chain. And we have the Markovnikov addition here because the secondary cation is more stable than the primary cation. The first step that happens in this sequence is for hydrogen to go and form the cation. Let me go ahead and draw this out. If you want to pause the video and see if you remember how to draw out the mechanism for this addition reaction, go ahead and do that. So remember that these pi electrons go and grab a proton. This is not a radical reaction, it's a polar reaction, a heterolytic bond cleavage. So we have both of these electrons going onto bromine, not one and one. Either one of the carbons could get the hydrogen. The more likely pathway is to have the primary carbon get the hydrogen, get the proton, and the secondary cation be formed. Because again, secondary cation is much better than the primary cation. And then the other thing that's formed is a bromide ion. One of the lone pairs on the bromine atom can go and attach itself to the carbon that is electron poor. Only has 6 electrons, not a full octet. I'll just draw the arrow over here. So this is the product that forms from that, the secondary alkyl halide. Your textbook does not mention this, but one of the videos I posted on Canvas at the time said that if you use peroxide, you get the anti-Markovnikov product. That's because this goes through a radical and not a cation. If you want to pause the video and try drawing the mechanism of what would happen when you add a radical to this alkene, you can give that a try. I guess that is this question over here. All right, so if you've tried it for yourself, let's go ahead and see what we came up with. So here we have this pi bond splitting in a homolytic fashion, one electron going to each direction. One electron is going to form that new bond to bromine, and the other one is going to just go onto a carbon. And so the two possibilities are for the bromine to bond to the secondary carbon, forming a primary radical, or the one that we have shown, the bromine bonding to the primary carbon, giving the secondary radical. This radical, the secondary radical is more stable, just as the secondary cation is more stable. So the difference is that the secondary cation forms by putting the hydrogen on that primary carbon. The secondary radical forms by putting the bromine on that primary carbon. So this is the more stable pathway, and then this would propagate by finding another molecule of HBr. That would lead to the hydrogen forming a new bond to that secondary carbon. And now another bromine radical is formed to attack another alkene in the mixture. So this only works for bromine, not chlorine or iodine. Let's just go ahead and have a review of what products would form. You don't have to draw out the mechanism, but just pause the video and make sure that you are able to draw the correct product that forms. So here are the products that form. A, B, and C all go through electrophilic addition, forming that cation intermediate on the tertiary carbon. And so all of these halogens end up connected to the tertiary carbon. We have some tertiary alkyl halides here. The peroxide goes through a radical, so the bromine adds first, forming the tertiary radical, which then gets a hydrogen. So we have the anti-Markovnikov product forming when you have a radical mechanism here, which only applies to D, the HBr and peroxide combination. Another useful way to get bromine onto a molecule is to put it onto the allylic carbon. You don't use HBr or Br2 for this because those would do the electrophilic additions that we learned in Chapter 6. So instead we have this N-bromosuccinimide reagent. It's a way to just give a little bit of bromine at a time so that we can, again, be more selective in where the bromine is going to go. So what happens is that the radical is created in this allylic position, and that's where the bromine goes. When the radical is created here, this actually is delocalized. So let's go ahead and take a look at this. All right, I'm just taking a look at figure 10.3 in your textbook to show what is happening in this allylic bromination. So the important point is that a bromine radical is going to create a carbon radical, just as we saw before. And it's going to create it in the allylic position because the allylic radical, remember, is way more stable even than a tertiary radical. And so that is the easiest place for the bromine to create that, that carbon radical. So there is a little bit of HBr that gets formed in this process. So there's not a ton of HBr around, which would make an electrophilic addition possible. So there is a little bit that's created in the course of this reaction, and then this small amount of HBr can react with some of the N-bromosuccinimide, some of the NBS that's around, and create bromine molecules as well. So there are some sources of HBr and bromine, but just not enough to cause electrophilic addition side reactions. So the radical reactions are going to happen more quickly. So this carbon radical that is created in the allylic position will be able to grab a bromine atom and regenerate bromine radical to keep this cycle going. So the important thing to take away from this is that the carbon radical is formed in the allylic position, and the bromine atom is going to add where that radical is created. Let's look at the positions where this carbon radical can be created. So we have this carbon, which is allylic. It's next to a pi bond. We have this carbon that is allylic, and we have this carbon that is allylic. So this first molecule actually has quite a number of possibilities of radicals that can be created. We have this blue possibility over here. Once this radical is created, the allylic radical is delocalized. So we could have this electron coming in, if you want to draw some arrows that show the different resonance structures. This blue radical here is actually partly there and partly on the carbon 2 carbons over. So we got the two-headed resonance arrow showing that this particular radical is delocalized. It's partly on this carbon, partly on this carbon. This particular radical is symmetrical, so once the bromine reacts, these are the same molecule, so it doesn't really matter which one you drew. Let's draw another possibility in green. This green radical is delocalized onto this carbon over here. It's right next to a set of pi electrons, and so those pi electrons can move into the p orbital of the radical. So remember, these pi electrons are in p orbitals. The radical electron is also in a p orbital. So we have 3 p orbital electrons right next to each other. So they're just sort of spread out over those 3 carbons. Each of these carbons kind of has 1 electron that belongs to it. So when this radical reacts, you can get both the bromine on the primary carbon like that, and you can get the bromine on the secondary carbon like this. Okay, so let's look at our third possibility. So this third possibility over here is this radical, which is delocalized over here to this spot, and that leads to these 2 products here. So this reaction might not be the best choice because we have so many different products that can be formed. We have 1 blue product, 2 green products, and 2 of the purple products. So 5 different allylic brominations that can take place with this particular compound here. All right, I think I'm going to have to erase some of these to try the second and the third examples. I'm thinking maybe I should have written these in the opposite order because C seems like it's the most symmetrical. It's going to have the fewest possible products, but I guess it was okay to start with the most complex one. Let's see if you can do the other ones. I'll erase these and give the answers to these in just a moment. For B, I've come up with two different possible radicals that can form, because we have an allylic carbon over here, this tertiary one, and we have an allylic carbon on the end, the primary one. So if the tertiary one forms, again, that is delocalized over these two carbons. So the bromine could be on the tertiary carbon or on the secondary carbon that's two away from that. If we have the bromine add to this, because remember the radical is distributed along this 3-carbon piece, so it's on this end and it's on that end. So the bromine can go either spot. If we have this delocalized radical, we have the radical part on this carbon, partly on that carbon, and so we could have these two products form from that. So we have these 4 that I've drawn. We also have the possibility of E and Z stereoisomers for some of them, so there could be even more of a mixture than what I've shown here. For C, we only really have one radical that can form. This, I've drawn 2 drawings down here, but they are actually the same because of the symmetry of the molecule. If you just take the second thing that I've drawn, rotate it 180 degrees either way, clockwise or counterclockwise, you have the same thing that I drew on the left. And so I just picked one of these to create the 2 products that can form. There's probably more than that because of E and Z possibilities. The ones that I've drawn, the E possibilities are going to form in a greater proportion because they are more stable. Okay, so we did already look at the text section 10.3 to figure out what the mechanism is for the bromination, but the important point to remember about that is that you are forming that allylic radical, which is then delocalized, which can form a couple of different products, the bromine in those different spots where the radical was. Okay, so this is a reaction that we're going to be revisiting. At the moment, I think the important point is to just remember that you can make alkyl halides from alcohols, and there are certain reagents that we have to remember to recognize, to know that that is what the reagent is doing. And so I have a little exercise here for you to practice seeing what those reagents are. Make sure you look them up in your textbook, have them in your reaction log. And you can pause the video to take a look at that if you like, and then I will provide them shortly. So here is the summary of reactions in the back of your chapter here. So if you have a tertiary alcohol, you're going to be using HX, so either hydrogen bromide or hydrogen chloride, to form that. If you have a primary or secondary alcohol, they would do better with these other reagents. To get the chloride, you would use something called thionyl chloride, SOCl2 in pyridine. To get the bromide, you would use PBr3 in ether. And then to get the fluoride, you would use HF in pyridine. So filling in those reagents over here, and also I'm being a little lazy and just using PYR for pyridine. For this tertiary alcohol, it would be better to use HBr. This is a primary alcohol, so this one you would want the PBr3. We could use that in ether. Oh, also for this one as well, you could put ether as the solvent. This happens very readily on tertiary alcohols. You can do this at a very cold temperature. This you need a little bit more of a reflux temperature. Your book lists 35 degrees, so that would be refluxing ether. temperatures for that one. Now that we know how to make alkyl halides, we can use them in a few different reactions. The main ones that we're looking at this chapter are reactions to form organometallic reagents. There are going to be other reactions using alkyl halides in some upcoming chapters. So 3 of the types of organometallic reagents we're looking at are Grignards, which use magnesium, alkyl lithium reagents, and Gilman reagents, which use copper. The powerful thing about these reagents is that it puts a negative charge onto carbon, and so then carbon can act as a nucleophile and attack different electrophiles. The electrophile that this chapter talks about attacking is an alkyl halide. So one type of organometallic compound that can be formed is an organolithium reagent. To do this, you need 2 equivalents of lithium and an alkyl halide. And you also need an inert solvent, an unreactive solvent like hexanes. Remember, alkanes do not react very readily. And so what happens here is that the bromine gets replaced by lithium, and then the other lithium goes with the bromine to be lithium bromide. We are not covering the mechanism for this reaction. We're just knowing that it is a way to make alkyl lithium reagents. Alkyl lithium reagents are pretty harsh, so this chapter is using them as an intermediate to make the lithium diorganocopper reagents. So this works with an aryl halide, so a halogen that is attached to a benzene ring. It also works with a vinyl halide. This chlorine is attached to a sp2 hybridized alkene carbon, and it also works with an alkyl halide. So we'll put this over here. Okay, and the main reagent that we are concerned with is the organolithium compound, not the salt, the lithium chloride or lithium bromide side product that is created. So this magnesium is usually a +2 when the magnesium becomes charged. And so what happens with a Grignard reagent is that the magnesium will insert itself between the carbon and the halogen. So it's almost like this magnesium is a +2 charge effectively. The bromine is -1 and the carbon is -1. So this is a Grignard reagent here. You can make this, again, you can make an aryl one. You could have a benzene ring attached to MgBr or MgCl. You can have a regular alkane like this one. Or you can also have a vinyl one. So we have a vinyl one, we have some alkyl ones. We don't have an example with a benzene ring, but you can make that as well. I'll put another example on the side. So I did not have this example listed in this problem, but I just wanted to make sure that people know that you can do this with a benzene ring as well. In fact, this one we are going to be doing in lab this semester. We're going to be making this Grignard reagent and reacting it. All right, and then finally we have the Gilman reagent. So we need 2 of these alkyl lithium reagents that we saw being formed above from lithium and alkyl halide. Once you have this lithium reagent, you can make a Gilman reagent out of it. The Gilman reagent has 2 of the alkyl groups on the copper. So we have a copper with a +1 charge, lithium with a +1 charge, and 2 of the carbon pieces, each of which has a -1 charge. The other lithium atom ends up with the iodide that came in on the copper. So here is one with a different alkyl lithium. We can make this Gilman reagent as well. And the lithium iodide is just a side product. That's not the important thing that we are worried about. We would be using the diorganocopper the lithium diorganocopper reagent, or the Gilman reagent. I've gathered a few details about Gilman reagents. The alkyl group that is on the copper can be methyl or a primary alkyl. We had some primary alkyl ones shown up here. You can also have an aryl, which is a benzene ring, or a vinyl group on there, but you cannot have a branching. You can't have a secondary or tertiary alkyl group. It's too hindered. This is a useful thing because it's a useful way to get aryl and vinyl halides to be pieces that attach to something. If you convert the halide, the aryl or vinyl halide, into the lithium reagent and then into the Gilman reagent, you can get it to attach to something else. So SN2 reactions that we are going to learn in the next chapter are ways to get alkyl halides to be attached to another piece and create a larger molecules. But aryl and vinyl halides do not do that, so turning them into Gilman reagents and getting them to attack something is a useful way to put these pieces onto larger molecules. Okay, if you have a vinyl group, if the vinyl group has a E configuration or a Z configuration, that would be preserved when you form the Gilman reagent. So if you wanted to attach an E alkene to something, you would use the E alkyl halide. Another detail over here about the Gilman reagent is that it's a very mild reagent. We're going to be learning about how a lot of these organometallic reagents react with the carbon of a carbonyl group, but this organocuprate does not react with carbonyls, and so you can react the organocuprate with a molecule that has a C double bond O bond, and you don't have to worry about messing with it, or you don't have to worry about ruining or losing this functional group. Other reagents, the organolithium reagents and the Grignard reagents, are more reactive, and they would react with the C double bond O group, so you cannot have a C double bond O group in your molecule if you're using a Grignard reagent or organolithium reagent if you don't want it to react. Okay, things that do react with the Gilman reagent, the lithium diorganocopper reagent, are epoxides. So epoxides can react. And also, these are things that you usually do not want to react with the organocuprate or with any organometallic reagent. You can't use them if you have water or alcohols around. So because this carbon is very basic, so when you have a carbon metal bond, the carbon is pretty negatively charged. So what happens is effectively you have this carbon with a negative charge. So it has possession of mostly possession of the electrons in that bond. So if you have any source of proton around, then what's going to happen is that lone pair is going to attach itself to that hydrogen, and then you just have a regular alkane. All right, so this is the kind of reaction that we would want to happen. So we would want to have a Gilman reagent over here. Here we have a vinyl one, and we are trying to attach it to this carbon that has a halogen on it. So we're replacing the halogen with this piece over here. All right, let's go ahead and label this. We have A, B, and C. So we have a 3-carbon piece that's being attached to this CH3 group. And the bromine is no longer there. So the bromine has gotten kicked off as a bromide. So there's also some lithium around. If you wanted to write this as a lithium bromide, you could. So there's some lithium around. And then there still is one piece attached to a copper atom. So these are really the side products. I'll put this in parentheses. The main product that we were trying to make with this would be to take this 1-carbon methyl bromide or bromomethane, this 1 carbon piece and then attach 3 more carbons onto it to create a 4 carbon molecule. So you can do make even bigger molecules than that, but that is what we're trying to do, is grow this organic molecule. This second one over here, what we are showing really is this Gilman reagent being ruined. So if there were water around, if there were some alcohol around like this, we have a fairly acidic proton with a pKa of around 15 to 16 for methanol, 14 for water. So this is way more acidic. This vinyl anion, if you think about it like this. So we have this carbon that has a lone pair basically. So it has 3 bonds, has a hydrogen over here. Here's the carbon, and it has a lone pair. Oops. So this carbon over here has effectively a negative charge. It has this lone pair of electrons. It's very basic. Vinyl carbons have a pK of close to 40 instead of 16 like this alcohol. So this would definitely be grabbing that proton, and you would have the carbon now with 2 protons, also just written like this. Then we would have methoxide missing a proton over here. So this would be an unreactive 3 carbon piece. So we took this reactive 3 carbon piece and created a less reactive 3 carbon piece. This did not attach to anything. It did not become a 4 carbon piece or become a longer chain at all. This is something that we probably did not want to happen. So that's why when you're working with these organometallic reagents, you have to be careful not to use alcohol at all as a solvent or have it in with your reagent, and also not to let water get into your reaction. The same thing would happen with water. You would have hydroxide instead of methoxide, but you would pretty much ruin your organometallic reagent. Okay, here's an example where we're conserving the stereochemistry of the vinyl halide, like we mentioned before. So since this bromine is on the same side as this 3 carbon piece over here, then when we attach the benzene ring, it's also going to be in that same position on the same side. So the Z configuration over here. So the copper is attached to a benzene ring. That is what's getting attached over here to that vinyl halide. And then again, our side products, we have lithium bromide, copper with just 1 benzene ring on it now. So these are both side products. We would not be as concerned with this. This is probably the molecule that we were trying to make. Here's an example of where this C double bond O is a fairly reactive group. It's a fairly electrophilic group, but this Gilman reagent is mild enough to leave this group alone and only go after the halide. And so that is where this piece would attach. We have an ethyl piece attached to our copper. So we would have this now. So here's our 2 carbon chain. It ends up over here. We had 1, 2, 3 carbons to start. Now we have 1, 2, 3, 4, 5. So we've added 2 new carbons to our molecule. Okay, so let's go ahead and try a reaction with an epoxide. We have seen a nucleophile opening an epoxide ring before. Last semester we saw a diol being formed by opening an epoxide ring with water. So an OH group getting attached, attacking the epoxide and opening it up. Let's go ahead and have this negative, again, effectively we have a negative carbon here. So if we treat this as if it is a carbanion, we can have this lone pair attacking this carbon here. The carbon already has 4 bonds. There's a bond to hydrogen that's not drawn. So we're going to go ahead and break this bond so that the carbon can only have 3 bonds. it's attacking from the other side. So this carbon-oxygen bond that's breaking is facing forward. That means the new bond that is forming is pointing backward. Now this oxygen has a negative charge on it. So this one over here, this carbon was already in the molecule. If we look at this as 1, 2, 3, 4, or maybe I'll label it A, B, C, D. So this is carbon A that just attacked this carbon that was part of the epoxide. So we also need B, C, and D here. So we have not done a lot of carbon-carbon bond forming reactions so far in this course. We are going to be doing a lot more. So you might want to develop some sort of trick to help you, or some sort of plan to help you be able to join these pieces together without losing any carbons. So if you have to give the carbons numbers or letters, or just count the total number of carbons in the product, make sure you haven't lost anything, then I would suggest you get into that habit so that you can have the whole complete molecule that you have made and not just some wrong pieces in there. Okay, so this is drawn a little bit differently than the one in the answer key, I was just realizing, but that's okay. This is also correct. So it could attack, I think the one in the answer key was because it attacked the other carbon and opened the epoxide the other way. This is a symmetrical epoxide, so either one can get attacked here. So let's go ahead and just keep with the one that we are doing. So when you first open the epoxide ring, this electrons go onto the oxygen, and so it has the lone pair. It's negatively charged. It actually has 3 lone pairs. Then one of these lone pairs can grab a proton from something. If you are lowering the pH, you have some kind of acid source around, so this lone pair can grab the proton and it can look like a regular alcohol after that. It's kind of strange to have the methyl group in this line here when there's a longer carbon chain. So if you want to, you can rotate this. So if you rotate around this single bond, you can bring, right now we have a hydrogen facing up. Let me draw that. We have a hydrogen atom coming towards us, like on a wedge. We have the butyl group going back on a dash, and then we have the methyl group in the plane of the paper. So we can twist this around, put this butyl group in the plane of the paper. That would push the hydrogen back, and the hydrogen would be a dash, and the methyl group would be coming forward as a wedge. So I put an equal sign here because this is the same molecule. It's just twisted, and this looks a little bit more normal to have the longest chain going left to right instead of having the longest chain going up and down and curving around like this. But either one is fine. Another type of organometallic coupling that uses a halide, not an alkyl halide, but an aryl or a vinyl halide, is called a Suzuki reaction, also known as a Suzuki-Miyaura reaction. This has already been, it's the same thing typed twice, so it's probably easier to read in this bullet point way. So I apologize for that. I didn't didn't proofread this well enough. But here is our list of features of the Suzuki reaction. The palladium catalyst helps to join a halide with an organoboron compound, so a borate ester. Your textbook also has like a boronic acid derivative. So the boron compound, the organoboron compound, can be any type of alkyl group or vinyl group or aryl group. And if it is vinyl, if the vinyl group is on the boron compound, the alkene that forms is going to be in the trans configuration, the trans stereochemistry. If you have the vinyl piece on the halide, then you will keep the stereochemistry in the product. So you can have either cis, you can have a cis halide if you want the cis alkene in the product, or you could have the trans halide if you want the trans in the product. They're pretty mild reactions, and so other functional groups are not going to be ruined by the borate ester and the palladium catalyst. And the palladium catalyst that's being used, I've seen it written a whole bunch of different ways. Your text has at least 3 ways written in this chapter. The previous text I used just had a generic palladium with 2 ligands on it, so L2 palladium. So your text at one point uses palladium catalyst for the reaction. So any of these types of palladium catalyst are okay to use. So here I have just the generic 2 ligand with palladium over here, and under slightly basic reaction conditions is what the previous textbook used for the Suzuki coupling. So what we have here is the alkene on the boron. So this is one of the commonly used borate esters. Here we have one with 2 methoxy groups. Here we have something with 2 alcohol groups and a benzene ring attached to the boron. The thing that's not on an oxygen, this carbon over here, that's the carbon that is nucleophilic, that is going to replace this iodine. So let's do a little practice again. If you want to number or letter your carbons, just to make sure you put all of them on there, they are going to replace this iodine. Also, since the vinyl group is on the boron, that is going to end up with a trans configuration of the alkene in your product. So let's draw the rest of this starting material other than the iodine atom. The iodine atom is getting replaced, and the iodine atom is getting replaced with a 4-carbon piece. The A carbon that used to be attached to the boron is now the one that's attached to this carbon. It's replacing this carbon-iodine bond with the carbon that is attached to the boron. So we have carbon A, B, C, D. The alkene is between carbons A and B. The alkene is trans, and so that is the correct product to form there. Here we have a 3-carbon piece that is going to add onto this vinyl halide. Remember, if the halide is the vinyl group, then this is conserved. So this is a Z configuration. We are going to keep the Z configuration in the product. So here's the Z configuration. Remember that we added 3 carbons, A, B, and C over here. So here they are. This is the piece that was there before. If you need to give these carbons numbers or letters in order to keep it straight, please feel free to do that. Okay, here we have this trans alkene, so we'll go ahead and keep that configuration. Instead of this bromine here, we are going to attach to this carbon over here that was connected to the boron. So that is part of a benzene ring. So this benzene ring is here. So we have 1, 2, 3 carbons and a benzene ring, 1, 2, 3 carbons and a benzene ring. So be careful not to insert some extra carbon in between there. So just to remind you, we've seen how to make boron, organoboron compounds before. We used them before as intermediates in a hydroboration reaction, and then we would oxidize the boron off and give alcohol as the product. But instead of oxidizing off the boron and making an alcohol, you could use this boron reagent to do one of these Suzuki Miyaura couplings. All right, so in order to get a vinyl group on the boron, you would add this boron and this hydrogen to an alkyne. Remember, a hydroboration adds a hydrogen and a boron to the same side of either an alkene or an alkyne. So this would have been an alkyne. Between A and B, there would have been a triple bond, and then you would add the boron to carbon A, the hydrogen to carbon B. So if you had this alkyne here and you did a hydroboration with this borane derivative, it's called catechol borane, then the boron would be adding to carbon A, the hydrogen would be adding to carbon B, and you would have this vinyl boron reagent that you could then use in a Suzuki-Miyaura coupling. This particular boron reagent would have come from a 3-carbon alkene. So if we had propene and then boron added to carbon A and a hydrogen added to carbon B, that would result in this alkyl borane that could be used in the coupling. You can't get a boron onto a benzene ring by doing a hydroboration. That is not the way it would be made. So in order to make an aryl borane, we would treat an aryl lithium compound with trimethyl borate. So if we had a benzene ring that looked like this alkyl lithium or aryl lithium compound, which we would get from either the bromine or the chlorine on the benzene, treating that with lithium like we did at the beginning of the section, we would get this lithium reagent. Then if we treated this with trimethyl borate, we would make this boron compound that could then be used in a coupling. The last section in this chapter talks about oxidation and reduction, how to tell whether an organic compound is becoming more oxidized or more reduced. In inorganic chemistry, if you see the charge on a metal going up or down, it seems like it's easier to count, do a counting on the electrons. For organic compounds, there's not as many times that the carbon has an actual charge on it, so you have to look a little bit more closely to figure out whether an oxidation or a reduction is taking place. Just to remind us what oxidation and reduction are, oxidation is the loss of an electron or electron density in general. Reduction is gain of electrons. So how would a carbon lose electron density? I mean, obviously, if it has a positive charge, if it has lost an electron completely, that would be a very oxidized carbon. But carbon can lose electron density by having a bond with a more electronegative atom, like oxygen, nitrogen, or a halogen. A carbon could gain electron density by having a bond to hydrogen. So a carbon-hydrogen bond has more electron density on the carbon. A carbon-oxygen bond or a carbon-halogen bond has less electron density on the carbon. So if you were looking at a specific carbon, trying to tell whether it was more oxidized or more reduced than another carbon that you're comparing it to, you could count the bonds to the oxygen, nitrogen, and halogen, all the electronegative elements, that you count those because that's increasing the oxidation level of the carbon. Then you would subtract the number of bonds to hydrogen, because having bonds to hydrogen decreases the oxidation level or the oxidation number of the carbon. So to compare the oxidation level of two compounds overall, you could just count the total number of carbon-oxygen, carbon-nitrogen, carbon-halogen bonds. Those would be counted towards the oxidation number. Those would be increasing the oxidation number. And then you would subtract the number of carbon-hydrogen bonds, because that would be decreasing the oxidation number. And then I encourage you to look at figure 10.7 in the text. It has a list of different functional groups and sort of organizing them into a spectrum of which ones are more oxidized, which ones are less oxidized, meaning that they're more reduced. And I just have a few examples here. If you'd like to pause the video and see if you can take a look at the different number of carbon-oxygen bonds, carbon-hydrogen bonds, and figure out whether these are becoming more oxidized or more reduced, or whether there's no overall change in the oxidation state of the compound. All right, so let's take a look at this one, the beginning compared to the ending. You are gaining more carbon-hydrogen bonds. So we have this C5H10 going to C5H12. I mean, there's more hydrogens than the two that I've drawn. I've just drawn the two new ones. But more hydrogens are in the product, and so these carbon-hydrogen bonds are increasing the electron density of the carbon, and so that is a reduction. So we have more electron density around the product than we did for the starting material. So more electron density, that is a gain of electrons, so that is reduction. All right, for this next transformation, we have the same number of hydrogens in the product, so we have the same number of carbon-hydrogen bonds, but we have some new carbon-oxygen bonds that have been added here. Since we are adding carbon-oxygen bonds, that is definitely an oxidation. If we wanted to, we could actually figure out the numbers, like it said over here, to compare the oxidation level of overall compounds. So we have 0 carbon, carbon-oxygen, carbon-nitrogen, carbon-halogen bonds, and we're going to have 10. So the starting material has a -10 overall for the oxidation number, and then the product has 0 oxygen bonds, 12 hydrogen bonds. So going from -10 to -12, that's a reduction in the state of the carbon. Over here, we have the starting material has 0 oxygen bonds, 10 hydrogen bonds, so we have a -10 for the starting material. Here we have 2 carbon-oxygen bonds, -10, so that gives us a -8. So we've gone from -10 to -8 in the oxidation number, so we've gone up, really, from -10 to -8 is going up, and so we've increased the oxidation number, so this is an oxidation. So if you like to do this kind of bookkeeping, you can do that as well. Let's go ahead and do the bookkeeping for this one also. So this one over here is a little bit tricky, I think. This is an opening of an epoxide. So we have hydrolysis. We're breaking this carbon-oxygen bond using some water. We're starting off with C5H10O, and we are ending with C5H12O2. And just looking at the compound, we have not really gained any carbon-oxygen bonds. So the carbons over here have not changed as far as this carbon is attached to an oxygen, a hydrogen, and 2 carbons. And in the product, it also has an oxygen, a hydrogen, and 2 carbons. So that has not really changed as far as the carbon goes. So we still have carbons with 2 carbon-oxygen bonds in the molecule. The thing that has changed is that the oxygen is they're different oxygens being bonded to the carbons rather than the same one, and there's more hydrogens on the oxygens. I'm not sure the bookkeeping is going to work completely for this one. I guess it will if you just be careful. So this starting material, you have 2 carbon-oxygen bonds, and you have 10 carbon-hydrogen bonds, giving us a -8. And then in the product, we have 2 carbon-oxygen bonds still, even though there's 2 oxygens. There's more oxygens in the product, but there's still those 2 carbon-oxygen bonds. And then we can't really count these 2 hydrogens that are bonded to oxygens. The carbon-hydrogen bonds, we have 1 plus 3, so that we have 4, 5, 6, 7, 8, 9, 10. So we still have 10 carbons bonded to hydrogens. So we have kind of the same oxidation state. So I'm going to put this as neither. We could call this a hydrolysis. So over here we have a ketone going to an alcohol. This first carbon has 2 carbon-oxygen bonds. They're the same carbon bonded to the same oxygen, but they are 2 carbon-oxygen bonds. And then we have 10 carbon-hydrogen bonds. So we have -8 overall for this compound. And then here we have only 1 carbon-oxygen bond. We're not going to count the oxygen-hydrogen bond, but we have 11 now of the carbon-hydrogen bonds. So we've gone down in oxidation number. That would be a reduction. So that is one of the main types of things that you can do to these ketones, is to perform a reduction and convert it into an alcohol. An alcohol is definitely a more reduced form of carbon than a ketone is. So let's do a little bookkeeping on this last one, the alkene going to the alcohol. This is one of our chapter 6 reactions. So this first one, we have 0 carbon oxygen bonds in the starting material. We have 10 carbon hydrogen. So that would be 10. Here we are -10, -10. Here we have 1 minus 11, so a -10. So we really have the same oxidation level in this alkene as we do in this alcohol. We have gained a carbon-oxygen bond, but we've also gained a carbon-hydrogen bond. So overall, we would call this an addition reaction. We would call it an addition of water. That's what we called it back in chapter 6. We did not call it an oxidation or a reduction. So this one would be neither. So this addition reaction, you're adding water to this alkene, but it ends up not being a reduction or an oxidation. So that's just a little look and a little practice at some oxidation and reduction, so that when we refer to reactions as oxidations and reductions in the future, maybe you have a little bit better understanding why we're doing that. I know we have already talked about some reactions as being oxidation and reduction, but this is a pretty good review of that.